So we've been taking a look at calculus and we've come to the stage now where we've reached turning points. Now turning points is really useful, very useful tool in both engineering and science. So we're going to be taking a look at some worked examples and see how it can be useful to us, and then hopefully you'll grasp the importance of it. So these are the kind of examples we'll be looking at in the various presentations I'm going to be doing. We're going to start with an introduction, and then we're going to take a look at a cylinder with an open top. So that'll be a cylinder where we want to achieve the minimum amount of material to get the maximum amount of volume. In fact, we'll be given a volume to work to. You'll see when we come to it. The next one will be the largest area that can be fenced off with a set length of fencing, and in that we'll be making an assumption that the shape is of a rectangle or square shape. And then we'll be taking a look at a closed top cylinder, so that'll be like the first example but with a top on. So there won't be much difference there, only slight subtle differences, but it'll be the same thing. We'll be looking for the least amount of material that we can use to achieve a set volume. Then we'll have a look at what's the largest possible volume we could get from a piece of sheet steel. So if you have a piece of sheet steel, a set size, you want to fold up the corners to make it into a box that contains, say, a fluid, for example. And then finally we'll just finish with an example of what's the maximum volume of a cone we could get if the height is tied into the radius by this proportion. Okay, so moving on. Okay, so what turning points? Well, let's have a look. We've got this waveform here of some nature, some plot of x against y, or y against x. Now the turning point is where the gradient is equal to 0. Anywhere where the gradient is equal to 0. So we've got a number of these here. So that's dy over dx, equals 0. Of course, you know by now that the whole point of doing differentiation is to find the gradients at any point as we move along the x-axis, or whatever this axis is along the bottom here. So when it turns, when it goes flat, we call that a turning point. So we've got a few here. We've got one that, let's use a solid line here. So we've got one there. Okay. If I put a tangent across it, we've got another one here, which I've missed. Let me just move that up a little bit, if it lets me. Trying to move everything. I'll tell you what we'll do. We'll do it again. Right, where's my lines? Okay, so we'll try that again. So we've got one here. Okay, and then we've got a couple of other ones that are subtly hidden away. So we've got one there. Well, there's supposed to be one there, and there's one there. Okay, and we give these names. So this one here is known as, let me just put my pen back on, this one's known as a maxima. Okay, this one here is known as, not very imaginatively, a minima, like a small Italian mother. Okay, and this is a big Italian mother. And these two here, we call these inflections. Now this has got two spellings, the way you'd expect, inflection or inflection, and you can find both spellings in the books. Now the difference here is this one, let's start with this minima, you've got a negative gradient on the left and a positive on the right hand side, so you get this U shape. With this one you've got the opposite, you've got the positive to the left and the negative gradient to the right, so you get this like a top of a hill, an N shape maybe, and that gives you a maximum. Now this one you've got a positive on the left and a positive on the right, so it's going up, flattens out, goes flat, and then starts again. So it's turned flat, we could say, and then started again. And obviously on this one here we've got the opposite, we've got a negative on the left and a negative on the right, so it's coming down goes flat, and then goes down again. Okay, so these are turning points. And you may say, so what? Well, as you'll see in a minute, it's a useful tool, and let's just get on with it, I think, with an example. Okay, so in this example, we want to use the least amount of material possible, but achieve a volume of 2,000 cubic centimetres. This container's got an open top, and as we'll see later, there's a different, we end up with a different formula when we've got a closed top. Okay, so if you think about it, you're given this job and somebody says, okay, it's got to hold 2,000 cubic centimetres. What's the least amount of volume area we can use, the least amount of material that we can use? Because obviously that saves money. If you use less material, it's cheaper. And if this was made out of, say, aluminium, an aluminium can, aluminium's quite expensive, then obviously you can make a big saving if you can just reduce the surface area by even a cubic centimetre. So let's have a look. So if you think about it, if you take the radius, you can have a very small radius. This is a bit of a poor image, but the one on the left, you could make this even a lot smaller. So this radius here could be a lot smaller than it's shown here. It could be like a long, thin straw. And to get the volume in, you'd have to have a really long straw. Now this one's the other extreme. So the radius is large. Okay. And if you think about it, that could almost be flat. In fact, it could actually be the sides could be so small that they're practically zero, or even zero. So then you'd have the biggest possible radius, but the volume would be zero. Okay. So we could plot this, and we get something like this nature, where this point here is our minimum radius, the optimum radius for the surface area. So if you think about it, this one's going to have quite a big surface area, this one's going to have a large surface area, and in the point here in the middle we've got the minimum amount of surface area to achieve our volume of 2,000. So what you'll notice about this plot is that we've got a turning point here. So we've got a minima. Okay, and later on what we'll do is we'll have to test to make sure that it's a minima and not a maxima. Could be the other way up, in other words. So it could be the opposite to what we want. Logic tells us it's not going to be that, but we still have to do a test just to be sure. We have to prove it, really. Okay, so how do we do it? So let me just move this up a little bit, get a bit more working area. So let's make a note, I'll just keep that on view. Let's just make a note of what we're looking for. We need a volume, let's just turn my pen back on. We need a working volume of 2,000 cubic centimeters. Okay. The beauty of working in units, standard units, any units, is you can, if we work in centimeters and we work the way through the process, when we get a distance for the radius r, it'll be in centimeters. So we don't need to. The first time I ever did this with students, I said, "Oh, I'll convert it into cubic meters," and it just made the numbers horrible. It's made big numbers. And it's always difficult converting cubic measurements into the other units anyway, because you've got to do everything's to a power 3 or a power 2 if it's an area. So the easiest way is just to leave it in the way it comes: cubic centimeters, cubic meters, cubic miles, whatever it is, and leave it that way, and then your answer is going to be in the same units. So our answer will be in cubics, it will be in centimeters, length will be in centimeters, area will be in centimeters squared. Okay, so we've got volume is 2,000 centimeters. So what we need to do is, what we're going to be looking for is, if you look at our graph up here, we've got, as the area changes, as the radius changes, so we're going to end up with this situation. We're going to have changing the area over the change in the radius. So that's going to what we're looking for. We're going to look for the point when it equals 0, when the gradient is 0. Okay, right, we need a formula. We need probably a couple of formulas. So let's get one for the area first. So this is the surface area of our container. So A equals, so if you're thinking of a cylinder, what have you got? You've got one, if it's an open end, one side's open, you've got a base, which is a circle. Okay, what's the area of a circle? Pi r squared. Pi r squared. Okay, what else have we got? Well, we've got the cylinder bit itself, the bit around the side. Imagine if you were making this out of a bit of sheet steel. You'd have to cut a bit for you that's going to be your cylinder part, the body. You'd have to cut it and then roll it up into a cylinder. So we've got to add that area. So we've got that. So how do we find that? So it's going to be the circumference times the height. Now circumference, as you're probably aware, is pi d, but we want to work in terms of radius because that's what our variable is. So that's 2r. 2 radius equals a diameter. So we've got 2, then we'll usually put the pi in, 2 pi r. Okay, so that's the circumference, and then we've got the height. So that gives us the size of a rectangle plate, basically, the area of it, centimetre 10 centimetres squared. Okay, that's the starting point. Now we've got a problem here. We've got radius, which is what we expect to get. Okay, but we've got a different variable, which is h. So therefore, we've got to convert the h into terms of a radius. How do we do that? We're going to use the formula for the volume. So the volume is found from, is the area of the bottom, the base, times the height. So that gives us what we had before, pi r squared, okay, times the height. So that's, this bit's your base, the area of the base, times the height, and that will give us our cubic centimetres of volume. Now we happen to know that ours is going to be 2000, so I can write that in. So what we're going to do here is we're going to rearrange this equation to get it into terms of the radius, and then we're going to substitute into the we're going to rearrange it to get it into terms of h, and then substitute that into this. So then we've got a formula that's purely in terms of the radius. Let me show you what I mean. Okay, so if I rearrange this, it's going to become, let's put a therefore, a little triangle, therefore h equals 2000 divided by pi r squared. Hope you can see what I've done there, a bit simple transposing. Okay, I can now take this and substitute it into this h, which will give me a new formula for A. So our area equals pi r squared, the area of the end, plus 2 pi radius, and then I'll put this in brackets. We've now got, substituting in this for h, we've now got 2000 divided by pi r squared, close bracket, multiply this in, do a bit of tidying up. You can see I'm going to have to move up a bit here, like this. Okay, so now I've got A equals, the area equals pi r squared, no change there, plus, if I multiply this in, I'll get 4000, 2 times 2000 gives me 4000, divide by, times the pi r, all divided by pi r squared. Okay, so now I can cancel out. This pi will cancel with this one, and this radius on the top will cancel with one of these at the bottom, so I'll just end up with a similar one. So in other words, what I've got here is this, pi r squared plus 4,000 divided by r. Nicely simplified. Okay, so the next thing I'm going to do, now I've got my formula, is I'm going to differentiate it, and then I can set the value to 0, find where the gradient is 0, and find out what r is. But we just need to rearrange it slightly. We need to get, we can't differentiate this in this term, so we're going to change it into this term. Let me explain. So we've got 4,000. So I'm going to bring the radius to the top, the r to the top, which will make it -1 using my laws of indices. I can now differentiate this. Let's move up a bit more. Like that. Okay, so now we've got our dA over dr equals, so what's the differentiation of pi r squared? So in relation to r, so the 2 comes to the front, multiplies into the front. Pi is a constant that we can't change. Well, we can double it obviously, and then it just becomes r to the 1. We don't put the 1 usually. Plus, well actually we're going to bring the -1 to the front, so it's going to be minus, it's going to change the sign. No other change will take place with our number, because it's times 1, -1, and then our radius, our r, will become -2. Okay, easy enough. So what we're saying now is, so what we've got here is when dA over dr equals 0, then 2 pi r must equal 4,000 over r minus 2. Okay, let me explain if I've lost you there. What we're saying is that all of this here would equal 0 when the gradient is 0. That means that that bit, for all this to equal 0, that term there must be the same as that term. So I've got that minus that equals 0, so they both must equal the same number, whatever that number may be. So therefore they're equal to one another. And then when I subtract this from this, I get 0. I hope you followed that. Okay, so I'm going to look for r, so I need to make r my subject. So I need to rearrange this formula. And the best way to do this is to bring my r squared minus 2 down to the bottom. So let me just do, let's do it neatly actually. Let's do it all. 2 pi r equals 4,000 divided by r squared. Okay, so do a bit of rearranging. I will get r to the 3 equals 4,000 divided by 2 pi. So what I've done is multiplied through by the r squared, so I've brought it to this side of the formula. I've divided through by 2 pi, which is brought it to this side. Okay, and then let's do some tidying up. What we're really looking for is a radius, so let me just move things up a bit first. Make some more space again. Okay, so let's have a look. So what we're going to do is do some more tidying. This 4,000 will divide by this 2, okay, to make it 2,000 over pi. And if I do a cube root of all this lot, this will make this r. So do a cube root of both sides basically. So what I'll end up with is r equals 2,000 divided by pi. Not divide by pi, divide by pi, but yeah, then the cube root 3. Okay, to get rid of this term here. Do a a cube root of both sides. Now if I put that in my calculator, it's a simple number crunching job. We get, apparently, when I look at my notes here, 8.6. 8.6, which is a number, purely a number, but we need a unit and it's in centimetres. Okay, so 8.6 centimetres. Lovely, nothing wrong with that. Okay, if you want to make a cylinder though, you need two measurements, don't you? You need to know the radius, or your diameter, and you need to know the height. So how do I find the height? Well, that's quite easy. I just go back to the top to my, so I've got 8.6, keep that in mind. Go back to this formula here, this one. So I've got this one here, so I need to find out what h is, so I'm going to substitute in my numbers. So I've got h equals 2000 divided by, let's have an equals in there. That's really wrong. It should be just equals 2000 divided by pi over r, which is 8.6 times 8.6 squared. And that gives an answer of 8.6. Surprise, surprise. I get the same answer for the height as the radius. So, whoops, I've lost my pen. So, 8, oh dear me, 8.6. That's gone off the screen, hasn't it? Let me move over a bit. 8.6 centimetres, and back to the pen would be a good idea. Centimetres. Okay, so far so good. Only one problem there though. If we look at our, oh Kevin, if I go back up to our graph, as I said earlier, do I know this is a minima? What's to stop it being, let's have a different colour. What's to stop it being this shape? Other than the fact we know it isn't because of common sense, how do we know it's not a maximum surface area, not a minimum? Okay, well there's a couple of ways we can test this. One way we can do is, we know that this is 8.6 at this point here. I'll just change this back to black. So we know this, let's zoom in, let's be crafty. Okay, back to my pen. Okay, we know that this here is 8.6. So what we could do is, if we move to the left, and we don't have to move far, so we move over here and see if we get a negative gradient. And if we move to the right and see if we get a positive gradient, that'll tell us it's that shape. Incidentally, if we've got a negative and a negative, it'll tell us we had an inflection. If we get positives, like this, if we move to the left and move to the right, we know we've got a maximum. And what do I mean by move to the left, move to the right? Well, I'm on about the numbers. So say for example, we take our 8.6 and take say 8.5, 8.4, even 8, 9 for moving to the right. And if I just zoom back out now. Okay, let's shuffle back. So if I go and put these into my initial formula here, so if I put my say 8.4 in here and 8.4 in here and do the maths, I'll get the gradients. Now I don't care what the number is, I only care about the gradient. Is it a positive or a negative? So if I put me 8.4 in there, 8.4 in there, and I get a negative answer, okay, so I get negative, then I know, and I go to the right and put a bigger number in and get a positive. That doesn't mean much. So I've got my shape like this. I've got this, I move to the right and say put in 9, and I get a positive. then I know I've got a minima, and vice versa if I get it the other way around, of course. Okay, now if I get two negatives or two positives, then I know I've got an inflection. So that's your best test. Now there actually is a shortcut way as well. Well, it's slightly a shortcut. It depends on circumstances. Another way of doing it is, what I can do is I can go back to my formula and I can differentiate it again. Let's move over this way a bit, see if I can make some space. If I differentiate this again, I will get this. Let me show you what I mean. So if I go, so it's d2a over dr squared. So I'm taking this answer that I got before up here, just simply differentiating it again. Okay, I'd get 2 pi, and then the minus I had becomes a plus. From this minus here, multiply that in, I'd get plus 8,000. To the minus 3. Okay, and again I realise I've gone off screen. Let's just shuffle that over some more. Let's get really plenty of space. I've got this result. So what does that tell me? Okay, now if I take my radius I got as an answer, which was 8.6, put it into here and do the maths, I'll get a number, obviously. Now I don't care, again, I don't care what the number is, I only care about one thing. Is it a negative or is it a positive? Now this has got a plus and this is a plus, so the answer is obviously going to be a positive number, so I'm going to get a positive answer. So if I get a positive, I've spelled that wrong I think, positive, yeah, positive, never been the best speller. If I get a positive, it's the opposite to what you think. It means it's a minima. I can't spell either. Minima. If I get a negative answer, where's my T gone? Then it's a maxima. Like that. Okay, so it's the opposite way around to what you think. If you get a positive, then it means it's a minima. If you get a negative answer, then it's a maxima. And the good thing about this is, what makes it easy is you don't really have to reach for your calculator, because as soon as I look at this, I know my answer is going to be a positive, because this is a plus and this is a plus, so it's going to give me a positive number. If this had been a negative and this had been a negative, then I'd get a negative answer, so then I know it'll be a maxima. If one's a negative and one's a positive, then it's a case of which is the biggest wins, so to speak. So, and you don't always need a calculator, because sometimes one of the numbers is massive and the other one's only small, so it's going to, you might be subtracting a very small number from a very big number, so it's still going to be a positive, and vice versa if it's the other way around. So you don't always need to reach for your calculator, so it can make it, this is why it can be easier. So I know that mine actually is a minima, so in other words, my shape's that shape, so my gradient is a minima. Okay, so on the next slide I'll look at some more examples and we'll see where we go from there. Thank you for listening.